In this module, we're going to look at modeling a non-stationary arrival process using Simio, and the example we're going to run is pretty straightforward. Let's think about having a hot dog stand that's open from 8 a.m. till 4 p.m. daily, and that we have some evidence, some historical evidence that shows that the hot dog stand serves approximately 190 customers per day, and the single server can handle approximately 240 customers per day. So let's think about creating a basic Simio model of this system. And so what we would do to start out is we would just say we have an arrival rate of 190 per day, and let's go ahead and convert that to an hourly arrival rate. And so we can take our daily arrival rate, 190, divide it by our time frame, which is 8 hours. And so this is going to be 23.75 customers per hour. And similarly, we have a service rate of 240 customers per day. And so this would be 240 divided by 8, or 30 cust per hour. And so when we look at this, we can see that we can process customers faster than they arrive. So everything looks good so far. And so let's look at how we would implement this in Simio, and then we'll come back and discuss the non-stationary arrival. So this will be a fairly easy model starting out. Let's just drag our source, our server, and our sink. We're going to model this as a single server queuing system. So let's just connect these guys up. We'll use paths here. Doesn't really matter whether we use paths or connectors for what we're going to look at today. And drag our model entity out. Run and make sure I got it all connected. Of course, I have a very simple connection, so hopefully I was able to do that. And everything looks good so far. And so now we can put the arrival and service process. And so if we look at our arrival process, if we have 23.75 per hour, that equates to an in-arrival time of 2.526 minutes. And let's just assume that we have a Poisson arrival process. So this is going to be 2.526 minutes in arrival time. For our service times, we said that we could process 30 an hour, and we don't really have any information about the distribution. So let's just use a triangular distribution. Again, this really doesn't have a whole lot to do with the problem we're looking at for this model. So we'll use a simple model. And if we operate at 30 per hour, that's a mean time of 2 minutes. So let's just do 1, 2, 3 minutes for our triangular processing time. And so now we have our model, and we can speed it up a little bit and watch it run for a little while. Again, we haven't really done anything yet other than specify the arrival process and the service process. So the next thing we have to deal with is the run time, the run length. And so we said in our problem description that the hot dog stand was open from 8 to 4, and so we have an 8-hour run length. But let's deal with the situation at the end of the shift. And so at the end of the day, rather than just closing it for what the hot dog stand would most likely do is continue to serve all of those customers that are in the queue. So what we'll model is we'll shut the arrivals off at 4 p.m. and then we'll continue to run until the last customer leaves. And so to do that, we can go to our source and we can go to the stopping condition and say that we want to run for exactly 8 hours, or we actually want the source to create entities for 8 hours. Then we're going to go to our ending time and set our runtime to be infinite. And so what happens here is that we don't have a specified ending time, but we shut off arrivals at after 8 hours, and so Simio will continue to run until there are no more entities and there are no more future events. And so if we run and then jump in fast forward, we can see down here at the clock that we ran for 8.02 hours. And so that tells us that the source instance stopped creating arrivals at time 8, but there was still customers, or a customer, at least one customer in the system, and that customer departed at time 8.02 and the system terminated. So now note that the closing time, or the time that the last customer leaves, will now be a random variable since we have random arrivals and we have random processing. So let's jump in and create a couple of responses just like we would normally we've done in the past. So let's go create an experiment, and since the closing time is actually a random variable, let's just create this response to show when the system actually closes. So we'll call this closing time. And we simply have to report the current runtime. So we can do run, let's just do time now. Time now. And so time now will then report the current time at the end of the replication. And so if I just do a quick run and look at our results, we can see that the average closing time was 8.0598. Of course, I can go and look at my SMORE plot as we normally do, and you can see the variation in the closing times. So that's an interesting way, a little tidbit here for this model, where we can shut off arrivals at a given time, but let the system continue to run until there are no more integers in the system. And so finally, let's create two more responses. Let's just create a response for the number in system. Number in system. So we'll just use the standard default entity, population, number in system average, and time in system average. Same basic response, TIS, and we'll do default entity, population, time in system average, and finally let's convert this to time, and let's just run in minutes. So we run in minutes, and now we reset, run, and just make sure that we have our two metrics specified correctly, and they look approximately correct. So let's go back and look at our assignment here. And so we see that we have implemented a very straightforward system, and the way we've implemented our source instance, we have implicitly implemented what's called a stationary arrival process, but that's just how we've automatically implemented it. So by putting our inner arrival time as 1 over 23.75, we specify that for the entire day. So starting at 8 o'clock and going to 4, we have that same arrival rate through the day. However, for a hot dog stand, it's unlikely that this is the arrival rate that it would actually see. In particular, it would probably see something more along the lines of this plot on the right, where the arrival rate depends on the hour of the day. So when the hot dog stands opens at 8, you have very small arrival rate, or very few customers, and that rises quickly as we get closer to the noontime rush, and then drops off again later in the afternoon. So instead of having this stationary arrival rate, what it most likely sees is something called a non-stationary rate, where in this case the instantaneous rate of arrivals depends on the time of day. To model our non-stationary arrival process, we're going to use what's called a piecewise linear approximation. And so if we look at this in Excel, you can see that what I've done is I've divided our day from 8 to 4 into hourly time blocks, and then we've specified a different arrival rate for each one of the hourly blocks. And so we say that we have 5 customers per hour from 8 to 9, 10 from 9 to 10, 20 from 10 to 11, and so on. And so you can see that this piecewise linear approximates our non-stationary process. So the next step is to tell the source instance that I'd like to use this non-stationary arrival rate. One note here is when we look at the times from a daily perspective, we're still operating at the same rate. So we still have 190 customers per day. We've just divided that into different rates for each hour. And so that's where we still have our 23.75 customers per day arrive to our system. And so what we want to look at now is how to implement this non-stationary arrival process in our model. So we can go back, and in our source, if we look at the source instance, one object or one property is the arrival mode, and we have used inter-arrival time to model a stationary process. Another option is the time varying arrival rate, which is exactly what we want. And when we select that, we see now we have an error saying we haven't specified the appropriate rate table. So we go back to our data and go to rate tables, and we're going to create a rate table. And you can see by default Simio pre-populates it with a 24-hour day and 1 hour for each one of the time slots. So I want to have my interval size of 1, but I only want to have 8 intervals. So I can then set my rates per hour according to our non-stationary rate. So if we go back and look at Excel, we see that customers arrive at the rate of 5 per hour during this first time period. So that equates to a 5 here during the first time period, then 10 during the second time period. So we have a 10 here, then we have 20, then 40, then 45, 35, 20, and 15. And then we will call our rate table, let's just call it customer arrivals, and then we can go back and address our error that we have just specify the table that we just defined. So now I have customer arrivals in our source that's defined by the arrival table. So now I can run my model. So let me go back and note that I have the speed factor set to 100, and we can run and watch. As we watch the hours go by, we will hopefully see that around the lunchtime that we will have a large increase in the arrival rate. So we're up here at 3 hours now, and we can see that it's starting to pick up from the queuing, and now we're up here at lunch, and you can see the queue build. Of course, in this environment, it's a little bit difficult to really see what's going on in terms of that arrival, non-stationary arrival process. So what we're going to do is we're going to quickly add a status plot so that we can watch, at least on the interactive run, the number of entities. So I'm going to create a plot here, and let's just call this number in system. And I want to have this run for my 8-hour run. Well, let's actually do a 9-hour run, because we again, we want to run till the system empties out. And what I want to track is, I'm just going to go for my expression and say the number of entities in the system. So let's just do our default entity population number in system, but instead of average, we're just going to do the instantaneous value over time. And so now when I run my model, we can see the number in system for any given time. Note, I didn't set my time, so I didn't set that the time starts at 8. I could easily just set the starting time to 8 rather than 12 a.m. And we can see now we're entering the lunchtime rush here, and we can clearly see that our number in system has significantly increased during this rush, and now it's dropping back off in the afternoon. So if we go back and look at our Excel, this is certainly what we expect, because recall the average arrival rate is 23.75, which is right around here, and at 11 o'clock and 12 o'clock and 1 o'clock we actually exceed the capacity. So we have a service rate of 30, but from 11 to 12 to 1 we have an arrival rate greater than that. So we certainly expect to see some significant queuing in that time frame. In fact, if we wanted to make sure that we had enough capacity, then we need to have the service rate be at least 45, at least during the noontime rush. And so we can see in our model, the implementation of the time varying arrival rate was very straightforward. What we first had to do is define the process. In other words, take the non-stationary process and define the piecewise linear approximation, which we did here, and then define a rate table within our model. So if we go to data, rate table, and we just specified the arrival rate. Note that one thing, when we specify the arrival rate, it's always in arrivals per hour. So regardless of what time units we're using, we always need to specify in terms of arrivals per hour in order to use the source object from the standard library with the arrival mode of time varying arrival rate. So another option we could do for the server is we could use a server schedule so that we have two servers potentially during lunch, and we can do that by setting the capacity type to schedule, but that's a topic for another module.